So first we need to introduce transformation properties. And we introduce transformation properties of the fields. The coordinates do not change under these U1 transformations. And the law of change of the field at classical level is the following. F go to exponent I qi alpha fi, and conjugate is transformed with minus sign here. So I here denotes the field, and it refers to field, and don't confuse with I, which is this usual complex. Now, alpha is a parameter, continuous parameter. So if alpha is function of x, so we call this symmetry local symmetry. Otherwise, it is global. So we make the same transformation by the same angle in all points of parameters of configuration space. Now, qi is something which is associated to a given field, kind of charge. And as we will see, in the case of conserved symmetries, that is the quantum number which is conserved also. So we have transformation, which is E I qi alpha. This is unitary transformation, so that the U dagger is 1. This is diagonal transformation. In a sense that it transforms field to itself with additional phase factor and not changing indices. The change of the field is when you have non-abelian symmetries like SU2, for instance. We have doublets, for instance, and then the symmetry transformation also transform up components of doublet to down component or to some admixture of these two. So another property of the symmetry, that this is abelian symmetry, which means that if you have transformation U alpha 1 by angle 1 and U alpha 2, so they can be permuted. So that will be U alpha 2, U alpha 1, and I assume that you actually studied this symmetry in the group theory course. So now let's go to quantum level. And by the way, this type of the transformation holds for fields with different spin. This is for scalars, for pseudoscalars, for vector fields, and for fermionic fields. The same type of the transformation. Now at quantum level, the transformation is, as we discussed already before, has such a general form. Now we can use dagger here because this is unitary matrix, and this is F I prime. Now at quantum level, U becomes operator, and we can write it as I Q alpha. Where Q is operator of charge. have consistency with classical transformation, and this is transformation at classical level, we require that U, so that the correspondence to classical transformation is U Fi U dagger equals E minus I alpha. So that's what we had at classical level. By the way, this equality can be derived. I mentioned already before, but let me just repeat. So since we have here continuous symmetry, we can use Nato Theorem, which tells us that if you have continuous symmetry, like this one, then there is a conserved current. And zero component of current integrated over space gives us, so there's a current, which is the function of the fields. And you know what is this expression for these currents. Then you take zero component and integrate over dx. That gives you the charge. When you go to a quantum level, this becomes operator, and therefore Q becomes operator. And what is staying here is precisely this type of the charge constructed out of the fields, operators of the fields. So using these and using Nato Theorem, you can prove this. Remember, each current corresponds to a generator of transformations. Here is just trivial, a single generator of transformation. Okay, and therefore we have just one current and one charge, and this charge corresponds to this trivial generator of transformations. Okay, so this is important. If you want, you can just consider this as really correspondence. That is how it is transformed at quantum level, by definition. And we want to have the same as we had at classical level. But now we announce these operators. Again, that can be obtained from theory. So actually, in the previous year, some time ago, I actually made this derivation, or even give some homework to prove this equality. Again, using the theorem, expressions for the currents. So you find what is the current, you find what is this charge, and then you insert in this expression and show that this is reduced to such a form. Now, let me use this equality and use this equality for infinitesimal transformation. So suppose alpha is much smaller than 1. Then what we have on the left-hand side is 1 plus I u alpha Fi 1 minus I q alpha. Right? So I have this exponent, and I just decomposed it. It's 1 plus or minus this I q alpha. On the right-hand side, I have 1 plus I q I alpha I. So I just have written this equality for infinitesimal transformation. Now, so I have several terms here. 1 and 1 is just cancels with this one. I will neglect the terms which are alpha square, and then the rest is just I q Fi minus Fi q alpha, and on the right hand side I have I q I alpha Fi. Okay, so I and I, alpha and I cancel. And what I will get is Q Fi minus Fi Q, essentially commutator, equals Qi Fi. Now let me act by this equation on the vacuum state. What I will get is the following. If vacuum is invariant, so if vacuum is invariant under this transformation, then Q acting on vacuum gives 0. So vacuum vanishes. So how I can get this? So let me take again. The symmetry of the state is expressed in the following way. Right, so this is the symmetry. But here I need to use my exponent. And for infinitesimal transformation, I will have 1 plus I Q alpha multiplied by 0 by vacuum state is vacuum state. So then this cancels with this, and I will get that alpha is arbitrary parameter. The Q acting on vacuum state gives me 0. So vacuum vanishes when I act by Q. This is different from what we had for discrete symmetries. This is because this Q is staying in exponent, in contrast to discrete symmetries, which are immediately act on the state. So here is Q which acts. I'm discussing Q and its action on the vacuum state. So if I would have here P, then it's the end of the story. But now this, what I'm studying is what is the effect of Q, and it vanishes vacuum state. So if I take this into account, then my equality becomes the following. So the second term cancels, and I will have Q Fi equals Qi Fi. Okay. So this equality tells me that the parameters Qi, which are staying in transformation of a given field, are actually the eigenvalues at quantum level of operator Q for the eigenstate Fi. So this is the question for eigenstates and eigenvalues of the operator Q. And so this equality tells me that Qi is the eigenvalue of the eigenstate Fi. Okay. So at quantum level, the parameter which I introduced in transformation law is nothing but quantum number. So that Q is now characteristic of a given state Fi. Now let me consider the system of fields and to see what are the transformation properties and charges of system of the fields. So essentially, I'm developing this formalism for U1, which we did already for other symmetries. So suppose we have the system of the fields, which is formed by action of F1, Fn, onto the vacuum state. As we discussed already, at quantum level, the transformation property is given by action of the operator of transformation on the state. So this is how the state is transformed. What I can do, and we did already the same trick before, so I'm inserting here one, which is U dagger U. In between of each of these field operators, including here U. Okay, then that becomes U F1 U dagger U Fn U dagger U vacuum state. Again, if vacuum is invariant, that this is just vacuum, and each of these blocks, according to our transformation rule, is reduced to I exponent in the power I Q1 alpha, then Qn alpha, and then F1 Fn. So, and this is nothing but exponent I, and then the sum over charges Qi. Which means that we can introduce total charge, which equals to the sum over the charges of fields which are in our system. And it's clearly that here, this Q is additive quantum number. In contrast to parities, which we have discussed, and the parities were multiplicative quantum numbers. And again, this is because our charge is staying in exponent. This is why we have here the sum and not the product. Okay? This we are discussing eigenvalues of operator which is staying in exponent. By the way, I haven't mentioned this Q should be Hermitian. And this follows from unitarity. So to have unitarity of U transformation, Q should be Hermitian. And again, the story is the same as we discussed before. If our theory is invariant under these transformations, then Q should be conserved quantum number, which means that Q total in initial state equals Q total in final state. As the consequence of invariance of our Lagrange or Hamiltonian of interactions. I will not repeat this analysis, is completely the same as we discussed before. This is one of the consequences of the symmetry. If the symmetry is exact, then you expect this equality, which is the consequence of invariance of the Hamiltonian, which is, let me repeat again, is this. So using these, taking this in between the states, initial and final state, so taking the matrix elements, you can show that you have non-zero matrix elements provided you have this equality of the charges. Questions? Everything clear? Okay. So let me now discuss applications of U1 symmetry. So in general, we have Lagrangian or Hamiltonian of interaction, which is the function of all the fields. In general, the theory on Lagrangian has many U1 symmetries. So the total symmetry is UA1 times UB1 times UN1. Different U1 symmetries are determined by charge assignment. And of course, the symmetries are different if, for instance, charge prescription for this symmetry is not linear combination of charges prescribed to other symmetries. So the set of the charges for different fields, for different U1, should not be a linear combination. Otherwise, you just reduce one U1 symmetry to another U1 symmetry. So this U1 symmetry is very often used even to forbid some interactions, where you very often people are introducing additional U1 to kind of forbid something which is unpleasant. Let me give you examples of these prescription, of different prescription. And I will take the following fields. I take proton, neutron, U quark, D quark, lepton, neutrino, and for instance, W boson, W plus. So those are the fields in my theory. And now let me prescribe to these particles the following charges of all for U1 symmetry: 1, 0, 2/3, -1/3, -1, 0, +1. So what is this U1 symmetry with these charges?
Electric charge.
Yeah, so it's U1 which corresponds to electric charge, Q. So we can have the following U1 with the following charge prescription: 1, 1, 1/3, 1/3, 0, 0, 0. So what is the symmetry which corresponds to this charge prescription?
Baryon number.
Right, so this is baryon number. So we may have U1 electromagnetic, or we can have U1B, which is baryon number. Simultaneously, in your theory, can be this symmetry and this one with these charge prescriptions, and clearly that they are linearly independent. So these charge prescriptions are linearly independent. So you cannot reduce a baryon number to electric charge. So let us consider next. Let me consider 0, 0, 0, 0, 1, 1. So, yeah. What is this symmetry? With this charge description.
Lepton number.
Lepton number, right? So this is lepton number. And you see all these symmetries. This is UL1 can be simultaneously. So the theory is invariant under U1 cross U1B cross U1L. And we can even continue to introduce more symmetries, more U1 symmetries. Let me discuss checks of invariance, or how exact the symmetry are. So let me first discuss U1 electromagnetic, which is related to electric charge conservation. The best check of conservation of this U1 is given by searches for decay of electron to neutrino and gamma. So this decay hasn't been found so far, and the best bound comes from studies of stability of atoms, right? So if this decay exists, then atoms will be unstable. The best bound is that the lifetime of electron should be bigger than 6.6 times 10 to the 28 years. Next, let us discuss baryon number. The best bound is provided by searches for proton decay. And tell me, suppose we will not keep baryon number. Suppose baryon number is violated. Can you suggest some modes of decay? How proton can decay? Suppose we have electric charge conservation, we have conservation of angular momentum, but not baryon number. So then, which kind of final state you can suggest?
3 pions.
3 pions. Let me see. So you have 5 plus 3, 5 plus 5, 0, right? Well, probably this decay exists. So in principle can exist, right? So you violate by a number. You can satisfy angular momentum. Sorry, it should be minus. That's good. Of course, you will have some violation of C parity, but maybe still it's okay. What happens is the strongest bound comes from the mode of the decay, such as for mode of the decay, P plus and pi 0. By the way, you see here you have only baryon number violation. Here you have violation of baryon number and lepton number, because in initial state we have a state with non-zero baryon number, and here we have lepton number -1. By the way, in this table I have written for particles, for antiparticles, the charges are of opposite sign. Now, in the theories, realistic models which have been constructed, actually, in most of them, B minus L is conserved. For instance, Grant unified theory is the simplest one, when we unify all the interactions about gravity. This is usually a good number, a conserved number. And therefore, it's more kind of realistic. And the bound is much stronger than from this, okay? So the best bound has been obtained onto this mode, and actually onto other modes also, by super Kamiokande. I will show you the pictures of super Kamiokande tomorrow. And the bound is that the lifetime for this mode is bigger than 2 and to the 34 years. This is very convenient mode of the decay. So that's studied by super Kamiokande, which is water Cherenkov detector. It's water Cherenkov detector. And you can see Cherenkov rings, which are produced by positron, and then gamma decays into two, pi zero decays into two gammas. So you have three Cherenkov rings produced by these particles. Gamma are converted into plus and minus. So you see three rings. And then you can reconstruct what is invariant mass. And of course, invariant mass should be given by the mass of the proton. So they haven't found this event. Although from time to time they are saying, okay, we have some candidates, but nothing was officially published, so which means that this is also consistent with background. Now, they looked also for other modes, like P go to P plus and a single gamma, like P go to mu plus and the pi zero. This is similar, but here we have mu plus. For this mode, the lifetime should be bigger than 7.8 10 to the 33 years. Now, the mode of pi decay into mu plus and k zero is typical mode of decay when you have supersymmetric models. So it's important here that you have strange quark, which is heavier, and therefore the probability is bigger for this channel, predicted one, than for that one. This mode is actually restricted by 6.6 10 to the 33 years. So there's also mode of proton decay into neutrino K plus. So also in supersymmetric models and with the same kind of lifetime. So in all these modes, we have delta B, change of the baryon number by 1 unit, but B minus L is conserved. B minus L is conserved. So take, for instance, this mode. In initial state, B minus L is 1. And in final state, B is 0, but we have a positron here, and therefore that gives us minus 1, because there's B minus L is minus 1, and therefore this is 1. So search for proton decay is one of the fundamental searches in particle physics, because that would really tell us a lot about what could be the further developments of the theory, a unification of different forces. And it looks like the simplest grand unified models are already excluded. One is to have supersymmetry to extend this lifetime, or to do something else. And the search for proton decay is the goal of hyper-Kamiokande experiment. So this is the future Japanese experiment in the place which is close to super Kamiokande. And so they start to operate maybe in 5 years or so. So it's under construction, it's approved, and so that will produce some results in your active life. So some of you may work on the results of this experiment, or you can even now work on possible predictions or suggestions for this experiment, what to search for. Search for proton decay is one of the main goals of this experiment. Apart from proton decay, there is another process. There are various processes, but one is very interesting, is N bar oscillations. So if baryon number is broken, then in principle, it may happen that neutrons are converted into antineutrons with the baryon number violation by 2 units. So there are some models, some constructions which actually predict existence of of this type of oscillations. Like oscillations of K0, K0 bar to B0, B0 bar. So just neutron go to anti-neutron. There are different searches of these transitions, and one is free neutrons. So you create the beam of neutrons and look for appearance of antineutrons. The bound obtained in this way is that the time of transition should be bigger than 8.6, 10 to the 7 seconds. This is something like 3 years. Now, of course, this transition can occur inside the nuclei. Imagine that you have nuclei, and one of the neutrons is oscillating to antineutrons. Then it will be a catastrophic event because antineutron will annihilate with other neutrons inside the nuclei. Nuclear will just explode, right? And that should be some spectacular event with a release of big energy. So searches for this gives the bound. So bound, let me put. Okay, so bounded neutrons. And for bounded neutrons, the lifetime is bigger than 2.7, 10 to the 8 seconds. So what is interesting that the bound here is not extremely stronger than this one, in spite of the fact that, of course, you have a lot of nuclei and you can consider huge number of nuclei and neutrons, and the bound is not so strong. And the point is, the reason is that this transition is actually, it depends on mass difference of neutron and antineutron. More precisely, the mass eigenstates, because if you have such a transition, neutron and antineutron are not the states with definite masses. This is common for all these kind of stories with mixing. And the bound in the vacuum, sorry, the mass difference in the vacuum is what determines the lifetime. Now, if your nucleon is inside the nuclei, then due to interactions with other protons and neutrons inside the nuclei, they modify this mass difference substantially, which actually suppresses the amplitude of this transition. So that's the point why we have the limit, which is, say, 1 order of magnitude, not even 1, so a factor of 3 or so, 4, stronger, but stronger. Questions? Okay. Well, the story is, I started to work in physics about the time when people discuss grand unification and this proton decay. And it was SU5 and SO10, very popular models of grand unification, which actually unify strong electromagnetic and weak interactions. It's very strong motivation. You know, it's really great because we have 3 different couplings at low energies. We have this intermediate bosons, gluons, W boson, photon, and they look like a different. And this grand unification actually allows you to put all these intermediate bosons in a single multiplet, say 24 plet of SU5. They allow you to reduce all the 3 couplings to a single coupling. And it is a spontaneous violation of this SU5, which actually leads eventually to 3 different interactions at low energy. So this is a great idea, absolutely great. And I remember that in the 80s, people were just thinking that we're about to discover proton decay. Discovery of proton decay would be great confirmation, because also in these grand unified theories, you put quarks and leptons in the same multiplet, so that quarks and leptons are different states of the same particle. This is really great, and this is one of the most beautiful things which were produced. But unfortunately, you know, it was 80s, proton decay was not discovered, 90s not discovered, 2000 not discovered, and so yeah, hang on that. So of course, discovery of the proton will give us a strong input how the theory should be developed. So maybe some of you will work on some grand unification with proton decay, which has long enough time. Some people are saying maybe there is no grand unification, maybe so the couplings and all the things occur somewhere at Planck scale, where also you can simultaneously include gravity. Then, of course, decay rates become very small, and then you can explain the fact that we do not observe yet the proton decay or baryon number violation. So let me discuss now flavor lepton numbers. So remember we discussed electron, neutrino, electron, muon, neutrino, muon, nu tau, and tau, and probably I will discuss, say a little bit about tau neutrino discovery at the end of this lecture or maybe next lecture. So we introduced three lepton numbers, Le, L mu, and L tau. So we introduced three different U1 symmetries, which correspond to these numbers, and made the following prescription: 1, 1, 0, 0, 0, 0. Here is 0, 0, 1, 1, 0, 0. So these lepton numbers are good lepton numbers once you consider decay processes. But then it was discovered that these lepton numbers are violated by oscillations. So that's what we will discuss soon. The processes which actually used to check conservation of these lepton numbers are mu go to E gamma. Remember, that was the process which was used to motivate to introduce another neutrino. And the lifetime is bigger than 4.2, 10 to the minus 13. And that is expected to be improved soon. Now, tau can go in principle into electron and gamma. That also has not been observed. And the bound is weaker, of course, because we have smaller number of tau leptons produced. So it's 3.3, 10 to the minus 8. So also there are processes like tau, which are searched for unsuccessfully yet. And the bound is 4.4, 10 to the minus 8 on branching ratios. So these are branching bounds on branching ratios. So I think, I know, once it's branching ratio, it should be like this, right? So the branching ratio should be smaller than these numbers. Okay? And nobody corrects me, come on. There are also other processes like mu-E conversion in interaction. So you may have a muon beam which interacts with nuclei or nucleons, and then you are looking for appearance of electrons in final state. also hasn't been found. So let me write here that we are talking about U1 E times U1 mu times U1 tau. And those U1s are conserved by weak interactions. So if you take Hamiltonian or weak interactions, Hamiltonians, which we have been discussed, or interactions of currents with W bosons, those interactions conserve lepton numbers, at least up to the accuracy we have achieved for today. Okay? Let me introduce now total lepton number. So these flavor lepton numbers, as I said, are violated in oscillations, and we'll discuss this tomorrow. So let me introduce total lepton number. Total lepton number is just sum over L alpha, and alpha is E, mu, and tau. So lepton numbers of neutrinos and corresponding charged leptons is +1, and for antineutrinos and antileptons, it's -1. So even if you have violation of flavor lepton numbers, like for instance oscillations of mu e go to mu, total lepton number is conserved, right? Because total lepton number is 1 here and total lepton number 1 is here. So you may have violation of flavor lepton numbers or individual lepton numbers. However, total lepton number is conserved. So this is more fundamental, so to say. Let me discuss violation of total lepton number. Actually, this is as important as searches for baryon number violation. Total lepton number. Violation of total lepton number is related with possible Majorana nature of neutrino. Have you studied Majorana equation or Majorana fermions at some of the courses? Okay, so in 30s, Majorana has suggested two-component fermions, theory of two-component fermions. So it was Dirac equation, which has described 4-component fermions, Weil equation, which described 2-component, however, massless fermions. So Majorana has introduced equation for fermions. He was not talking much about neutrinos, he also mentioned neutrino, of course, but the most economical equation for fermions. He constructed his Majorana equation in 1936. The Torah Majorana, 1936. according to Majorana, neutrino coincides with antineutrino. So this is why it has 4 components, right? Because we have 4 component Dirac fermions. We have different polarizations and fermion and antifermion. So here the number of degrees of freedom just 2, not 4, as for Dirac fermion. This is because this additional condition is realized, that neutrino coincides with antineutrino. So neutrino is truly neutral particle, as we discussed before. Neutrino coincides with antineutrino. Let me discuss this issue in the following way. First, introducing Majorana mass terms. So let me remind you that for fermions, we have mass terms in Lagrangian of the following form. So I refer this to the fields or wave functions. So this is the mass term in Lagrangian. For bosonic field, we have m square, f square, right? And for fermions, we have this stuff. Now, we can decompose, as we did before, nu into nu left and nu right components using projection operator 1 of plus minus gamma phi over 2. I will not repeat this again. Inserting this expression into mass term, we will get mass nu left, nu right, plus nu right, nu left. And other terms, because you have 2 by 2, 4 terms, and other cancel because of projection properties of 1 plus gamma phi and 1 minus gamma phi, right? Because if you have left, you do conjugation, it will becomes right, and you have right and right here. That's fine. So again, for Dirac fermions, nu left and nu right can be considered as independent components. Looking at this expression, we conclude that Dirac mass connects left and right components. So this is an important feature of mass terms. You can consider this as a coupling which transforms left components to right components. So for instance, this term corresponds to nu left, which appears from nu right. So nu right is transformed to nu left. And this is described by M. That's like you can consider as transition, as interaction, which is given by mass. So mass is parameter which tells, gives you the transition probability from transition amplitude between left and right and back. So let me invert argument and to say the following. To construct mass term, you need to have left and right components. The same is for all fermions, for electron, muon, quarks, for everybody, right? So if you have Dirac fermion, or any fermion, sorry, so any fermion, to have mass term, you need to cook it from left and right component. Now, in the case of electrons, for instance, so left and right components can be considered as independent particles and states, and you have this four-component theory for Dirac fermions. Neutrino is special, and neutrino is neutral. And we can construct right-handed components. Suppose we just use left component. Suppose we take nu left. Can we construct mass term just using nu left? Can we use only left component, which means that we deal with two-component theory, right? So can we construct mass term? And we have no right-handed component of neutrino. The answer is yes, and we can build up the right-handed component using nu left and performing charge conjugation. You will have exercise to check this. If you have left-handed component and make charge conjugation, it becomes right-handed component. Therefore, we can construct the mass term using the following. We take mass term over 2. Then we use this nu left C and make Dirac conjugation. Nu left plus Hermitian conjugate. So here the factor 1/2 appears because now we have less components, right? Less degrees of freedom. And when we compute equation of motion using this Lagrangian, it will be factor of 2 when we will differentiate, because this is essentially nu L, right? So nu L squared. We can rewrite such a mass term. We can write this as m/2 nu left transponent C minus 1. This is I gamma 2 gamma 0 nu left plus Hermitian conjugate. And T is transponent. You see here, there are double conjugation because we have C, and C is done by doing Dirac conjugation, and then we do again, and therefore this block reduces to this nu L. Simply. Questions? And again, this factor 1/2 is that when we are going to obtain equation of motion from Lagrangian, right, using Lagrange equation, we are doing differentiation over different terms, over degrees of freedom. And to get correct value of mass in equation of motion, we need to put here 2, because we have here nu and this nu, and when we differentiate nu squared, it will give me 2, and therefore in equation of motion you will get normal value of mass, which is this one, m. Questions? So if there's no question, then I will ask question. Why we cannot not do this for electron? Or for muon? Just take left-handed component of muon, make charge conjugation, and write mass term for this. So why it is not possible? Come on.
It will violate U1 of electromagnetic.
That will violate electric charge, correct? Because if you do this for electrons, then you will get here EL and here EL. So, which means that this term in Lagrangian will have double electric charge. And terms in Lagrangian should be neutral, because then you compute matrix elements. And the presence of charge, electric charge of L, would lead to the processes when charge will change by 2 units, right? So that type of term of Lagrangian would violate electric charge by 2 units. So this is why we are not able to write this for electrons, for muons, for other particles, but neutrinos. And we can do this by for neutrinos, because neutrino is neutral particle, and it has no coupling color, and therefore it has no conserved quantum numbers. And therefore we can write this for neutrinos, but not for other particles. So neutrino is special in this case. But actually, probably because of this fact, neutrinos are much lighter. Actually, there's a nice mechanism which connects smallness of neutrino masses with this feature that it may have such terms in Lagrangian. You will have exercise, but more in detail you probably will study in the standard model course. So we have this term. It is constructed with 2 components of fermion. So we just use left-handed. There is no right-handed. So in this theory, we have left-handed neutrino and right-handed antineutrino. Okay. So it's 2 components. It violates lepton number by 2 units. But we don't know if lepton number is absolutely conserved or not. So this term violates lepton number by 2 units. So lepton number is 1 here, and so the lepton number of this operator is 2. And therefore this term will violate lepton number by plus 2 units, Hermitian conjugate by minus 2 units. And so lepton number can be violated by mass terms. We think that hasn't been yet discovered. Now, what is connection to Majorana neutrino? So Majorana neutrino is introduced as nu, can be introduced as plus nu c. Or since we are using 2 components, it can be written as nu L plus nu C, and that will be the right component. Clearly, this state satisfies Majorana condition, because C conjugate of this state will give again the same state. So let us find what is mass term for this Majorana neutrino. How it looks like. As for any fermion, we write mass term as m/2 Majorana conjugate. Yeah. Now, I will not do this, but I'm asking you to do this. So if you insert into this expression for Majorana state given by the sum, and use projection properties of 1 plus gamma 5 and minus gamma 5, you will arrive precisely to this expression. So which means that this term, which we have introduced, corresponds to mass term of Majorana neutrino. Conclusion is that it corresponds to Majorana neutrino. So again, you just take this and insert into this expression. And you will get the masses, mass term which we have introduced before. Well, actually, you can introduce neutrino mass term in different way. So neutrino mass, Majorana neutrinos in different way. You can introduce Majorana neutrino as nu minus nu c. Under C transformations, nu m prime C will give you minus nu m prime. So additional sign minus appears. Or you can do even in more general form. You can introduce Majorana neutrino. So let me put here this way. You can introduce it as nu plus phase factor. And then under transformation, and then Majorana condition will be nu m prime C equals minus kappa nu m. So this is more general form, right? So if kappa is 0, then you have standard. If kappa is pi, then you will have minus sign here. Okay? So this is more general stuff. And what is interesting, this phase, which we call Majorana phase, has physical meaning, very important physical meaning. Actually, if you insert this in the mass term, then what will happen that this factor should be attached to masses. So in this case, the mass term is I kappa m, which tells us, I think with minus sign, please check this, which tells us that actually mass terms are complex in general. Again, this phase which I have introduced can be attached to just to mass term. And therefore, again, in general, Majorana masses are complex parameters, which again plays an important role. Now, how do we test the theory that neutrino is Majorana or Dirac particle? And this is one of the biggest problems in particle physics, actually, these days. So what is the nature of neutrino? Is it Dirac or Majorana? And how do we test this? Questions, by the way. So I will give you the exercise to check that, that this general definition of Majorana state with phase, it corresponds to mass term with complex phase. But this is simply just use this definition of Majorana mass terms, nu m prime prime, include a mass term, and then you will see that this phase doesn't disappear, so the phase is not cancelled, and that it can be attached to the mass term of Majorana neutrino. So tests of L violation and Majorana nature of neutrino. These tests, and the most sensitive tests, are studies of so-called neutrinoless double beta decay. Let me introduce what is this, and first of all, I want to introduce double beta decay. What is double beta decay? Double beta decay is the decay of nuclei into another nuclei which has electric charge by 2 units bigger than the original one, and emission of 2 electrons and 2 antineutrinos. It can be minus sign also here. So there's double beta decay plus and double beta decay minus. Then you will have here appearance of positrons, 2 positrons, but mostly that has been studied. So how it can be? Remember that in usual beta decay, Z changes by just 1 unit. We have 1 electron and 1 antineutrino in final state, like in case of neutron decay, for instance. So that happens because in nature, there are systems of nuclei for which usual beta decay is forbidden. So it may happen that for one of the nuclei, and let me take example germanium-71, which is very well used for researchers, then the nuclei which has charge by 2 units bigger, which is selenium-76, but the nuclei which is by 1 unit bigger than this, which is arsenic, it has bigger mass than germanium-71. Oh, 76, sorry. 76. So, of course, this is forbidden, but this is allowed. So it's because of, and this is mass scale, this is because we have such a system, the usual beta decay is forbidden, and only double beta decay can exist. Actually, it can be such a configuration. It can be configuration when the intermediate nuclei is not very heavy or even comparable mass, but the spin is very strongly different, and therefore it's just very strong suppression due to difference of the spins between a nuclei of this type. So double beta decay was proposed by Keppert-Meyer in 1936. Many events happened in 1936 actually. And you have just a nuclei in which 2 neutrons, undergo beta decay. So it go to proton and then emit neutrino and electron. And this happens with the second one. Independently. Of course, this is very strongly suppressed, because you need to have really simultaneous occurrence of these 2 decays. And this is actually, this rate is proportional to G to the 4th, G Fermi to the 4th power, because you have two decays here. So it's proportional, the probability to G Fermi to the 4th, And typical lifetimes are bigger than 10 to the 20 years. Okay? This is a double beta decay. Now let me discuss neutrinoless double beta decay. If neutrino is Majorana particle, then what may happen is that neutrinos emitted by neutrons do not go outside, but they annihilate inside the nuclei. So what happens is that neutron is transformed to proton, emits antineutrino, then another neutron and also electron, which goes out, also produce proton, electron, and again antineutrino, and then they can annihilate in the case of Majorana nature. Or you can say the following: antineutrino, because of it coincides with neutrino, then you have neutrino, which actually is absorbed by neutron and emits electron and proton. So essentially for Majorana neutrino, you can consider the mass term when you have nu bar annihilating in one point, right? So this is a mass term, Hermitian conjugate from what we have discussed, but this is present. So mass term for Majorana neutrino can be considered as interaction which produces annihilation of antineutrinos, two antineutrinos, or neutrinos. And this is what happens here. So what may happen that neutrinos are not going out, but they are absorbed inside, and what is going out is just two electrons. So this is the origin of the name neutrinoless. Neutrinoless. So you still have the same transition as we discussed before, but without emission of neutrinos. So let me draw this diagram of the transition in the following way. So you have neutron, which is transformed to proton, emits electron, and emits antineutrino, or absorbs antineutrino, or absorbs neutrino. So another neutron do the same, it produces proton, E minus, and we have this absorption of a neutrino. And this is because of Majorana nature, so we have this type of the transitions. Or again, we can make a transition when antineutrino is transformed to neutrino, and it's absorbed in the, so this is neutrino, and it's absorbed in this second vertex by second neutron. Okay, questions? So this is the diagram for neutrinoless double beta decay. One important point, we have not just one neutrino, we have three neutrinos. We have three neutrinos. So here we need to put index I and sum everything over 3 mass states of neutrinos, right? For each of these states, clearly that the amplitude of this process is proportional to the mass, Majorana mass of neutrinos, the amplitude of this process. And this way we can measure Majorana mass of neutrino observing neutrinoless double beta decay, because its probability is proportional to the Majorana mass squared. Of course, theoretician invented some other mechanisms of neutrinoless beta decay with some exchange of heavy particles here. But the most probable and the first place what you want to do is to just explore neutrino properties. Okay. So we introduce so-called effective mass of electron neutrino. By the way, the point is that here in the vertex we have G Fermi when we emit electron neutrino and not mass state. And therefore we have this mixing parameter, EI, right? And the same is here. I will discuss this in more details tomorrow. This is similar to what we have in quark sector. In the quark sector, we have the CKM matrix elements, and the same here in the tonic sector, which connects mass states, right? So here we have this UEI, and here is UEI. What is important that they are not conjugate, so that enters square, and therefore we can introduce the mass, effective mass, which is given the sum over the mass states, UEI square multiplied by MI. So we introduce such a parameter and say that probability of beta decay is proportional to MEE squared. So actually what we are probing is this combination. Now we know that the mixing exists, so we must write this type of the combination. Another subtle point, that these masses are in general complex parameters. Because of these Majorana phases. And therefore, it can be some cancellation here, because some mass is positive, another one is negative, for instance, right? And therefore, you may have some cancellation. So even though the masses can be Majorana, but you may not see it because you have a strong cancellation. So this is one of the problems in this type of the studies. Now, how do we search this neutrinoless double beta decay, and what are the results? So I mentioned already this germanium 76. This is one of the elements which people are using. And the setup is the following. You study this germanium decay. And germanium decay into what is this selenium, right? So I forgot already what I was saying. Yes, in selenium. So we are looking for germanium 76, go to selenium 76 plus E minus. So that's decay. What we are measuring the number of events. Of course, we do not see neutrinos. And what we can measure the distribution of these events over the sum of E minus two electrons. So we measure the energies of each of these electrons and sum up, and we get total energy in electrons. So the problem is the following. Of course, if neutrinoless double beta decay exists, that certainly usual beta decay exists, double beta decay, and that has the following spectrum. So this is for 2 beta 2 nu, usual double beta decay, number of events. And it is continuous spectrum Because part of the energy is taken by neutrinos, right? We have 2 electrons in final state and 2 neutrinos. 2 neutrinos are taking some of energy, and therefore the distribution is like this. For this process, there is no neutrino, and therefore the sum of energies of 2 electrons is just given by difference of masses of nuclei. So it's fixed, and it's at the end point of the spectrum. So you expect for this process to see peak here in the end of the spectrum. So overall picture is the following. You observe continuous spectrum of 2 electrons, and hopefully you will see some peak here. So the problem, of course, that this peak is not like this, but it is like this, and you always have some background because there's a tail of usual beta decay. So this is nightmare for experimentalists. You need to have very good energy resolution. Because the question is, if you have good energy resolution, then you can have a good sensitivity to this peak. If the energy resolution is bad, something like this, then of course you have big contribution from just usual beta decay. Okay, so this is one of the elements which was used. Another one for which the best bound has been obtained is xenon 136, which can decay into barium 136 and plus 2 electrons. But also tellurium has been studied. But this gives for time being the best bound of the lifetime, and therefore of the mass of Majorana mass of neutrino. So what you get here is that the lifetime is bigger than 1026 years, which can be converted into bound on MeE. So it's upper bound on MeE. And this is between 60 to 165 milli-electron volts. People also are using tellurium to search for this decay, and SNO experiment, which was used before to measure solar neutrinos, now converted to the experiment for searches for neutrino-less double beta decay. So what is this? This is quite close to what we expect from actually from neutrino oscillations if the spectrum is degenerate. I will discuss this in more details tomorrow. So this is the bottom line. Actually, there's a whole industry of these neutrino-less double beta decays. There were a huge number of different experiments because everybody wants to discover this total lepton number violation and establish the nature of neutrino. It's not a joke because if neutrino is Majorana, then you probably deal with seesaw mechanism of neutrino mass generation, which gives also a kind of a window to very high energy scales. So behind this measurement, there's a lot of things important. It's not just establishing what is the mass. Questions? And again, experiments are planned, and also a new generation of experiments are planned, and so that is the story for all the seasons. So it's already starting from 60s when the first searches have been done, and there are plans of future experiments with bigger and bigger mass of material which you are using, and with lower and lower background, and with better and better energy resolution. So these are the factors which are important for searches for neutrino-less double beta decay, and maybe some of you will work actually this is very important also experiment to search for new physics. Because if there is some new physics which produces total lepton number violation, then it can manifest itself in such an experiment. Also, the problem is that suppose you will see the signal, suppose you will see this peak. It's not immediate that you say, oh, these are neutrino masses, Majorana neutrino masses, which actually provide this decay. One still needs to work and to prove that this is neutrino mass and not something else. It may be just some new interactions which violate lepton number. So it's kind of complicated story, in fact. So what is left is neutrino oscillations, which I will discuss next lecture. Maybe a little bit I will mention discovery of tau neutrino very shortly. But there's some interesting thing. Nobody was actually in doubt that this tau neutrino exists. The experiment was in the year 2000, so not very long time ago. And but mostly it will be flavor mixing and neutrino oscillations for the last lecture. Okay?
One thing, what is the meaning of having a complex mass for the neutrinos?
That's complex parameter. Who told you that this should be real? You see, in many cases, it's just mass dagger what enters. Here is interesting, since you have something which is the mass, and you have several terms. Suppose you have just one term, one mass term. So let me say, in general, it's a complex parameter, the mass. What you see in the propagator is a mass moduli square of mass. It doesn't affect your propagation. Okay? But in some cases, this complexity is relevant, like here, because you have here terms, and what you compute moduli square of all this expression, right? And therefore, relative signs here, or even phases, do matter. So this is one of the interesting and important cases where this phase, which is called CP phase, actually neutrinos, because under C transformation you also change left to right. So that people are saying these are CP phases, and you can find even more formula in the following way. It's mi moduli and then exponent minus so plus I kappa r. So actually what matters is the relative phase of different terms. Actually two independent phases enter here. So relative phases between different masses. So this is one of interesting cases where complexity of mass can have a physical effect. Observational effect. Not for electrons, for electrons. So it's important that this is Majorana also. We do not introduce Majorana phases for Dirac particles, right? And always it's moduli square. Okay. Okay, so then see you tomorrow. Maybe someone will come.
Thank you.
And I will explain, maybe we'll tell a little bit about the exam.
right? So that how we will organize. I'm still thinking because for me it's also new to organize the exam in this way, and it's not clear. Maybe the center will be on lockdown, so that's also a possibility, by the way. But I cannot even enter this. We cannot enter the building. For time being, I haven't heard. There should be some decisions today, tomorrow, but most probably it will be something up to January 7. So it should be open if nothing drastically changes. You know, that's okay. Tomorrow, last effort. You know, remember that after that I will ask you. So you have last chance to ask me. And, you know, check my knowledge. Then I will ask you. Okay.